Any software that becomes sufficiently complex needs a database to manage all of its records. Today we talk about the history of databases, why they're important, and how they work. Welcome to Kopek Explains Software, the podcast where we make computing intelligible.
Well, this week, Dave, we're taking a more foundational look at software, and we're going to talk about databases. So let's start at the beginning. What's a database?
So if we look at the dictionary definition of a database, which might not be that useful, it's a structured set of data held in a computer, especially one that is accessible in various ways. Now, that's such a broad, such a vague definition that it really doesn't help us that much. And in fact, that's not that far from what the technical definition is that you'd find in a computer science textbook. Databases are for what we use when our data gets sufficiently large in terms of scale, when it gets sufficiently complex in terms of hierarchy, when it gets sufficiently rich in terms of the attributes of each record. If we have very simple data, we might just store it in a file. And by that very broad dictionary definition that we looked at, basically any file is a database because any file is generally structured and any file is accessible usually in multiple ways. But that's not helpful to us if we're really thinking about what people typically mean when they say database. When they say database, they usually mean a software system that has an ability to manage hierarchy for large amounts of data and query that data to get interesting records out quickly. And so when you hear the word database software, people are typically talking about sophisticated pieces of software used for managing large amounts of data and querying it.
So is a database a part of a piece of software or is it a separate piece of software?
So generally, sophisticated database systems are actually separate pieces of software that the software that a programmer is working with communicates with. So there are two different kinds of main database systems. There are server-client systems, where the software often actually sits on another computer, and the computer software that is connecting to it is considered the client, and the database management system is the server. It gets requests in a query language and responds with records. And there's also embedded databases that are actually built right into the piece of software that is being written. And that might be through a library, or that might actually be through an additional object model that gets thrown into the main piece of software. So we have embedded databases, and then we also have client-server databases. And when you're looking at web apps, almost always they're working with a client-server model, where there'll be another piece of software, the database management system, that might even run on a separate computer and get connected to by the web app. And then when you're looking at data for something like a smartphone app, you're more likely to see an embedded database, a database system that actually sits right there on the device with the software running. It might even be a part of the program. So depending on really the type of app that we're building and the sophistication of the data, how many records we have, we're going to see either a completely separate piece of software or a piece of software that gets embedded within the main software.
So that's part of the software engineers or the programmers' job in the beginning when they're working on their application is to decide what type of database software they want to use.
Yeah, it is their decision, and most of the time it's a very easy decision. There's kind of an obvious pathway. There's one very, very popular embedded database now that's used on so many different systems, from desktop apps to mobile apps, even sometimes to web apps, called SQLite. And we'll talk more about specific database systems later on, but it's extremely widely used. It's built into iOS, built into Android, actually built into most web browsers now. And then there are many different popular client-server databases. People might have heard of some of them, like MySQL, Postgres, Microsoft SQL Server, Oracle, IBM DB2. These are some of the most popular client-server model databases. And there's many different kinds of client-server model databases. All the ones that I mentioned now are what are called relational databases, and we'll talk more about that a little bit later. But there's also a whole range of newer client-server databases things that are called NoSQL databases, and we'll talk about what that means in a few minutes, but maybe people have heard of some of them, so I'll mention a couple. Things like MongoDB, CouchDB, or Neo4j.
Let's take a step back. Who first invented the database, and when did they come into being?
So because databases have such a vague definition, I don't know that we could even go and say who invented the first one, because we can define so many different standard ways of storing data as quote-unquote databases by the definition. But the first relational databases, which are the most common kind of client-server databases today, were created by Edgar Codd, or at least the theories for how to create them were created by Edgar Codd in 1970, and he worked at IBM in the 1970s, which at the time was by far the dominant computing company. And relational databases are all about how we can store data in tables that have connections to one another, and actually connections between the records within the tables as well, and connections even between the attributes that are in one record within one table.
So they have relationships to each other.
They have relationships, and the reason it's called relational, though, is because it's all backed by an actual type of mathematics, a type of algebra called relational algebra, which defines the system of how the records are stored, and yes, the relationships between the records. And so you can actually take all the operations you do on a relational database and break them down into their fundamental relational algebra components. And you can almost think about relational algebra as a whole separate math system. It's built out of some math that is well known for a long time, like set theory, but it is actually its own entire mathematical system. And so there's some really strong theoretical foundations to relational databases, and Edgar Codd was the person who developed those mathematical foundations, which led to the first relational database. And the first relational database came out in 1976, and it was developed by IBM. And then the next really big relational database, which is still with us today, was developed by Larry Ellison and co-founders of Oracle Corporation. And of course, the database, which a lot of people I'm sure are familiar with, is called Oracle. And so IBM and Oracle were the pioneers in relational databases.
So when we say that like Oracle made the first or one of the first like databases, we're
not saying that. We're saying they made one of the first relational databases.
Sorry, yeah. Because
the term database is so vague, we can't really say who made the first database, but we can certainly say who made the first relational database. And Edgar Codd invented the ideas, and then IBM and Oracle developed the first products.
So these products provide the structure for storing this information. They're not just collections of information itself.
Right. They are a system for systematically storing large amounts of information in a richly structured way that you can then later on query and get interesting records back or add records to or update records. And so they allow us to do large data manipulation operations in very efficient ways. Mm-hmm. And if you had to recreate that from scratch every time you wrote a new software program, you would spend all your time just building that part of the program instead of using these products off the shelf. So these products are integral to basically every sophisticated piece of software that gets written today.
So we have relational databases. What are some of the most popular relational databases that are getting used today?
So we already mentioned IBM DB2, and we mentioned Oracle's database called Oracle. And those two databases are proprietary databases, meaning that the source code is not distributed and people cannot kind of look under the covers and see how they work, and they're always sold for money, right? But actually, they are no longer the most popular databases. Oracle is still quite popular, but actually the most popular databases today in the relational side are all open source. And if people don't know what open source is, you can look at our previous episode, What is Open Source? And I'll put a link to that in the show notes. But the most popular databases today are things like MySQL, Postgres. I already mentioned earlier SQLite, which is an embedded database. Those databases are by far the most popular databases used in web apps, let's say today. And SQLite is the most popular database in the world altogether because it's embedded in so many different devices and so many apps. And they are actually all free, both as in freedom, meaning that you can do whatever you want with the source code, and you can go change them if you need to for your particular use case. And they're also free as in price. They're all freely available. Now, some open source software actually does have business models behind it. For example, MySQL was developed by a corporation that Oracle actually bought. So Oracle actually bought several pieces of open source software over the last couple of decades, and they happen to own the rights to MySQL. So even though that's not their proprietary database, Oracle is still, even with the combination of their proprietary database and MySQL, arguably by far the largest player in databases. But anyway, so those are a bunch of the most popular databases, and your typical web app is going to be backed by something like MySQL or Postgres. I think getting into the details of how each of them differ is beyond the scope of our podcast today, but they're all relational databases. So they all have that underlying mathematical theory of relational algebra behind them. And they all also use a query language called SQL, sometimes just pronounced SQL, which stands for Structured Query Language. It's a standard that was developed back in the late 1970s when those first relational databases were developed. And so because all of these different databases, MySQL, Postgres, Oracle, IBM DB2, all use SQLite 2, all use the same structured query language, the same SQL. Once you learn how to manipulate data in one, you can go and translate those skills to manipulating data in any of them, which is a really powerful thing. It means that data is portable. It means that practitioners of databases are able to take their skill set and make it portable between different relational databases. And also SQL just happens to be a pretty relatively easy to use programming language compared to a lot of other programming languages. And it means that even people who are not programming experts can generally do some basic queries in a relational database.
So there's relational databases, but there's another kind.
Yeah, there's a whole set of other databases, and the bad thing about the group of other databases is that they're often categorized by what they're not instead of what they are. And so they've really come to be popular over the last decade or so, and the whole group of them is generally called NoSQL databases, meaning that they don't use that query language. Mm-hmm. And they're generally not relational databases. And again, what a relational database is a database where we store records in tables. Those tables have relationships between one another. They sometimes have constraints between one another, and the records are also defined in terms of the relations between the various attributes of each record and the record and various records themselves. So that's how most databases work, is using these tables and using SQL. But this whole set of new databases that don't work that way are just categorized by being not built that way. And so then there's actually all kinds of subcategories within the realm of NoSQL databases. And the most common subcategories that they fall into are document-oriented databases, graph databases, and key value stores. Those are probably the three most popular categories. There's also other categories like columnar, but if we were just going to talk about the most popular categories, those three categories would cover most of NoSQL databases.
And what do those three categories mean?
So a document-oriented database is probably the easiest to think about. It's, instead of storing everything in separate tables and then having connections between those tables, why don't we just dump everything that's related to one another in one place? So put all the records for one thing in one place. Mm-hmm. It's a kind of simple idea, but it has a bunch of trade-offs, actually. You might think, wow, that just sounds better than chopping up the data, putting in different tables, and connecting it all. But it actually has some disadvantages too, such as you have less predefined structure than what you get when you break up data into separate tables. And so it can be prone to more kinds of difficulties when you later on want to update the data. But there are benefits oftentimes in terms of performance, whereby reading the entire document at once, you can maybe have faster reads than you would when you're looking through multiple tables and then assembling the data that you need back together. So there's trade-offs between document-oriented databases and relational databases, but document-oriented databases have probably become the most popular alternative to relational databases over the last 15 years. And the leading document-oriented database is called MongoDB. And full disclosure, I'm a stockholder in MongoDB. But MongoDB is actually taking the place of relational databases in a significant number of web applications, but it's still nowhere near as popular as something like MySQL or Postgres.
So why would someone choose a non-relational database versus a relational one?
Yeah, it really depends on the specific application and how sophisticated the data is. So if they, first of all, they're losing using SQL generally. And SQL is that standardized language that so many people already know. And it happens to be, in my opinion, a pretty good language for what it's used for. And so you're losing that. And then some people, think that actually there can be improvements on it. And so you're getting a different query language with each of the non-SQL databases. And some of them people might think are better and some of them people might think are worse. I talked about that performance trade-off. So that's generally going to be the main reason. The main reason people generally switch is because for the particular type of data they're storing, maybe it's not as richly structured, or maybe it's structured in a different way than lends itself to being in separate tables that are connected to each other. For those reasons, there's some performance benefit to going to a non-SQL database. There's also some other types of NoSQL databases we should talk about. So key value stores, you can think about as probably the most simple of all databases. All we really have at our bare bones in a key value store is a connection between keys, which are, you can think about them as like names for something, like something we want to look up by, and then values, which are whatever is associated with that name. And so you can think about
a decoder, or like a key to a map.
Yeah, and you can think about it like, kind of like a key to a map. I like that analogy. But you can almost think about it as instead of having multiple different tables that have relationships to each other, we just have one giant table. Mm-hmm. And the table only has two columns. One column called key and one column called value. And of course, there can be more structure than that in reality, but that is the simple basis. And then we just have some key we want to look up and we get back the value. So for example, if I was looking up data on people in a US government database, maybe I'd be looking up that data by their social security number. So the social security number would be the key and the data, all the data about them would be the value. Key value stores are more simplistic, but they can also, because they're so simple, they can also be very, very fast. And so if you don't have highly sophisticated structure to your data, a key value store can make a lot of sense. And then another kind of NoSQL database is a graph database. Graph databases are built on a different type of math, not relational algebra, but graph theory. Which is how we divide.
So we're not talking about like the bar graph or line graph.
No.
You think of when you hear the word graph, maybe.
Yeah, no, we're talking about the area of mathematics known as graph theory, which is all about how can I take the world and break it up into nodes that are connected to each other, and how can I look at, and those nodes are usually called vertices and the connections are called edges, but how can I look at how each of those nodes goes from, how we go from one node to another node. And so if you think about like networks in the world, like your electricity network, right, in your neighborhood, each of the homes you can think about as a node, and then there's wires that form the connections from one house to another. Or you think about a transportation network like the subway system in New York City. You could think about each of the individual stations as a node and the tunnels connecting one station to another as the connections, right? Well, what is some like common applications today that are like that? Well, an obvious one is social networks. Obviously, they're a network. You can think about each of the people in the social network being a node and who that person is following or who they're friends with being a connection. And so if I want to make queries about networks, graph databases are specifically optimized for that. So if I have data that lends itself to being described as nodes and connections between nodes, then I might want to use a graph database. And one of the most popular graph databases today is called Neo4j, and there's an emerging query language standard, so like an alternative to SQL for these graph databases called GraphQL, stands for Graph Query Language, obviously. So again, depending on the type of data that we have, we may decide on a non-relational database. But the default is still relational databases. So the vast majority of apps still being built today are still using relational databases. They're well understood. They're highly performant. They've been around for 30 years. And there's a lot of different relational databases. There's a lot of competition, and there's a standard query language, SQL. So the default when you build a new app today is to use a relational database. But if you have a good reason for using a NoSQL database, at least those other databases exist now. And there's a lot more we could get into in databases, but I think this is a good place to kind of leave people off with some links in the show notes to get into some of the specifics of these different kinds of databases. But databases, the takeaway for everybody is that anytime you have an app that has any kind of sophisticated amount of data, it's not going to just be using files generally. It's going to be going to the point of using a separate piece of software called a database management system. That software may be embedded in the app, like in the case of SQLite, or it may be running on a different computer even, in a kind of client-server model. And it's going to be responsible for richly storing all of that data in a way that's easy to query so that the app can actually retrieve records efficiently and not have to handle all of that data manipulation on its own. All right, Rebecca, how can people get in touch with us on Twitter?
We're at Kopec Explains, KOPECEXPLAINS.
And I want to thank everybody for listening. Don't forget to leave us a review on your podcast player of choice. And if you have ideas for topics that you want us to cover on the show, you can always send us a tweet at Kopec Explains, like Rebecca said. And we look forward to seeing you next week.
Thanks for listening.